Warning: the video you're about to watch contains mathematics at the level of pre-calculus. All material has an assumed prerequisite of college algebra and trigonometry. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello everybody, welcome back. We are going into probably the deepest part of pre-calculus here. So prior to this, you should have watched my videos. Well, maybe I should say prior to this, you should have already gone through sequences and series in your pre-calculus course. Is it necessary to know sequences and series for mathematical induction? Absolutely not. But that's typically what happens, is that you go through sequences and series and then you end up in mathematical induction. So what is mathematical induction? Well, you're starting to head to calculus. You're starting to open up that door into the world of calculus. And as you do that, you have to get used to proofs. You've seen proofs since your algebra days. You should have. Your instructors should have demonstrated proofs for you. And you should have already started engaging with proofs. For example, my students have done something like prove that a polynomial only containing terms with odd powers is an odd function, that type of thing. But those are called direct proofs. Direct proofs have this kind of nice nature to them, where somebody makes a claim, and the claim goes like this. If P is true, then Q is true. P and Q are called propositional statements. So if P, some claim, is true, then Q, some other claim, is true. If it's raining, then it must be cloudy, something like that. And when you do a direct proofs start at the beginning, the P part, in this formal if-then structure. The if part is called the antecedent. The then part is called the consequent. And in a direct proof, what you do is you assume the antecedent is true, and you do some logical deductive work to end with the consequent. And those arguments are generally based on definitions and previously proved theorems. It's a very clean way to build a proof, but it also can be very challenging because there's not like some structure that's built for it. It's incredibly loose. It's very artistic. It's actually the most artful form of mathematics. And because of that, that can be very difficult for new students to mathematics. There are many styles of proof, and some of them can be more artful than others. For example, like I said, the direct proof is a very artful form of proof. A proof by contradiction is yet another one. It's a beautiful way to prove, but you essentially say, well, suppose that P, the antecedent, is not true. Then you argue, again, through logic and generally supporting yourself through definitions and previously proved theorems. You argue that therefore Q could not be true. In other words, the world blows up, or there's some type of logical fallacy that sneaks its way into your argument, and the only assumption you had at the very beginning was P was not true, therefore P must be true. There's also a proof by contraposition. So again, this list is not endless, but it can grow pretty massive. However, the one we're going to focus on here is a proof by mathematical induction. And proofs by mathematical induction really are proofs based on arguments, or for arguments based on the natural number system. Let me write that down. Proofs by mathematical induction are generally used when a claim, which is also known as a conjecture or hypothesis, relies on the natural number system. This is not necessary to actually cover the entire natural number system. It could start at 5 instead of 1 or something like that. However, the claim really does rely upon a set of positive integers, generally speaking. Now, before we could talk too much about it, I need to actually define a few things for us so that we have a common language. We'll start with what looks to be functional notation, and it actually kind of is. P of x is what we're going to call that. It's not a polynomial, which is what I would normally use for the capital letter P, but it's called a propositional statement. And that propositional statement could be that, oh, it's raining, for example. That's a propositional statement. It's raining, right? It could be true or false. So P of x is a propositional statement that is either true or false. So I'm driving. I'm not, so that's a false statement. So this is what the language we're going to use. Our propositional statement with mathematical inductive proofs or mathematical induction proofs is going to rely upon the natural number system. So we're going to say like, is P of 1 true or false? In other words, is a statement true if I plugged in 1? Is P of 10 true or false? Is our statement true if I just plugged in 10? So I just want to make sure that we have that written down first. The next thing I want to talk about is dominoes, actually. So we're going to let go of mathematics for a moment, and we're just going to talk about playing a game of dominoes. If you don't know what well, it's not a game of dominoes, but if you don't know what dominoes are, they are those rigid, usually, unfortunately, ivory stones that you can stand on end, and you can knock them over, and they'll knock over the next domino and the next domino and the next domino, right? So hopefully you know what dominoes are. That way we can all kind of agree. Anyhow, so let's suppose that you have a set of dominoes. You want to stack them and maybe knock them over or something like that. Well, the big question is, if you had 1 billion dominoes all lined up to do some big patterns, snake around and stuff like that, right? If you just knocked over the first one and walked away, how could you guarantee that all the dominoes would eventually fall? Again, you start at that first domino, you just walk in this room and you say, I'm gonna knock this domino over, and before it even strikes the second domino, you're gone. So you're just gonna flick this domino right here, and it'll start to fall, and you run out of the room as fast as possible. Now, the question is, how do you know that the next domino will fall, and the third, and the fourth, and so on and so forth down the line, and it hits some arbitrary domino here, just some random one, and the next one, and so on and so forth, forever and ever and ever. And that arbitrary domino, it's very common for us to label that K. It's the kth domino. You don't know if it's the billionth, or the 100,000th, or the 15th, or the second. You just don't know. But anyway, it doesn't really matter. The fact is, you flick the first domino and run out of the room. How do you know that all of them are going to fall? You're trusting it, right? Well, let's suppose that after you flicked that first domino and left the room, now, like I said, there's 1 billion or maybe 1 trillion or a Google, that amount of dominoes, right? There's just more dominoes than you can ever imagine. And you've already flicked the first, you've run out of the room. And then about an hour later, you're like, you know what? I wonder if it's really going to knock all those dominoes down. So you decide to come back into this massive room, I guess, and you arrive somewhere down the line and you say, man, look at that kth domino. It hasn't fallen yet, but let's suppose that it does. I need to be able to guarantee the next domino in line falls. So it's sort of like you making sure that each domino is in position to knock the next one down. You're going to assume that kth domino is falling, and you want to show that, or at least convince somebody, that the next domino in line must fall. So what I have actually shown you here is the proof by mathematical induction. You are going to start by flicking that first domino. And what I mean by flicking that first domino is you're going to prove that whatever conjecture they're making, let's say they tell you, it would be nice to have a solid statement here. So let's say they tell you that if you add 1 to itself n times, that it will become n. Okay, let's just say that's the claim. That's a silly claim, but let's just say it is, okay? So you'll start by saying, well, if I only added 1 to itself once, then it is 1, right? So you've proven that claim, right? And then you run out of the room. And hopefully, when you add 1 to itself twice, it becomes 2, or 1 to itself 3 times, it becomes 3. You're just trusting. You run out of the room, and then maybe an hour later, you come back and you say, well, this domino hasn't fallen yet, So the other dominoes are still falling, but they haven't reached this domino. But let's assume that this domino is falling. I'm highlighting in red because we're not proving it. We're assuming that one is going to fall. And with that assumption, let's prove that it has to be the case that the next domino in line must fall. Okay, so now I'm going to zoom out. We will have proven that the first domino is falling. We're going to assume that the kth domino is going to fall and use that assumption to prove the next domino has to fall. Because k was arbitrary, in other words, we didn't specifically enter the room to look at the trillionth domino or the 100,000th domino or the 15th domino. Because k was arbitrary, k could be any number. Specifically, k could be 1. And if k is 1 and we prove that the next domino has to fall, then the second domino has to fall. But again, k is arbitrary. So if k is 2, then the next domino, which is third domino, has to fall, because we've proven if k is falling, then the k plus first domino is falling. But if the third domino is falling, well, we've proven that if any domino falls, the next one in line must fall, so the fourth one is falling, and so on and so forth down the line. And so this showcases that all dominoes will eventually fall, because no matter what, once one is falling, the next one has to. So essentially, you could think of it this way. We have to start the motor by proving the first one falls, period. There's just no way around that. You have to show that at least you can get it started. And then say, well, now if an arbitrary domino is falling, the next one in line, you're going to prove that the next one in line has to fall. All right, so let's bring this back to mathematics, and I'm going to erase that silliness down below. And let's just pretend somebody hands us some statement. They say, prove this propositional statement is true for n in the natural number system. That's what that n double bar is the natural number system. So they say, prove this claim is true for all natural numbers. The first thing you're going to do is prove that you can actually start the dominoes falling. So you're going to basically prove that the statement is true for n equals 1. And there are some authors, and actually it is actually true in logic, that you would basically say you want to prove p of 1, that p of 1 is true, right? So your propositional statement is true for n equals 1 is the same thing as saying p of 1 is true. Again, you definitely want to prove that statement. Now the next part of this, so that's us knocking down the first domino. We've proved that the first domino is going to fall. Then we just run down the line or leave the room and then come back an hour later and get to an arbitrary kth domino. And we're going to assume the statement is true for that arbitrary kth domino. And so I've written it as assume the statement is true for n equals k. And that is just you saying p of k, the proposition is true at k. And there's no need to prove that because you're assuming that. You're just saying, well, let's suppose that red domino there falls. Now using that, by the way, that in mathematics is called the induction hypothesis. I'll write it off to the side. Using that induction hypothesis, we will then try to prove that the next domino has to fall. Let's zoom in and write that down. And there we have it. Just use our assumption that p of k is true to help prove that the statement is true for n equals k plus 1. That is, we want p of k plus 1 to be true. And this we have to prove. So I'm going to just point an arrow at that and say prove it. We have to prove that. Once we've done that, we will have proof that no matter where we look, if a domino is falling, the next one has to fall. And because we've proven the first domino is falling, that implies the second one has to fall. But because now the second one's falling, the third has to fall. And because the third is falling, the fourth has to fall. And so on and so forth down the line. That proves that all the dominoes will eventually fall. Because once one is falling, the next one we have proven the next one has to fall. So that is the idea behind proofs by mathematical induction. And in the next video, we'll actually go through a plethora of summation examples, because there really are two styles of problems when you use mathematical induction. One of the most popular styles is for summation problems, when a sum is equal to something. Somebody claims that. And then the other style is for non-summation, so there'll be a second video for that.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.